Okay, everybody good to go? Everybody still awake? Good. Let's see if we manage to stay that way. So I'm Philip. I want to talk about some machine learning, some hyping, some making fun of stuff. So let's see where we can take this. So I work for Elastic, the company behind Elasticsearch, Logstash, Kibana, like previously called the Elk Stack. Now we call it the Elastic Stack. I'm part of our infrastructure team. I always say in the middle that is a Unix pipe. I kind of piped it out into developer advocacy. So I try to speak a lot about the good stuff that we do. And why am I talking about machine learning? Well, every company needs to have some machine learning in their stack. You can see we have kind of hidden it on the right-hand side at the bottom there, kind of like we have something about cloud, we have something about machine learning, like all the usual stuff that you need to have. We'll get back to that later on. But at first I want to talk a bit about machine learning in general and what it is and what it is not and what it could do for you. So some month ago, there was this like machine learning is going viral and everybody was going, oh, we need machine learning. We need to do more about that. And one thing about going viral was also that who remembers that iOS bug when suddenly the eyes were exchanged for a different character? That was actually machine learning as well, because that was kind of Apple added some machine learning for the keyboard that it would replace specific characters or words. And that was kind of as soon as you received that bad eye, which was replaced by some other character, that was already machine learning at work, because then your system would learn that other way to write or replace that term. And only once you received such a changed eye, then you would be or would do the same, or your device would do the same thing because your device had learned that. So that was kind of the power of machine learning, which was kind of a bug and like kind of a bit of a virus since it was spreading like that. But yeah, machine learning is kind of going viral in that regard. Yeah, and then there are always the people who are saying like, oh, we are doing some very fancy technology, even though we probably would have just needed a few if statements, which would have been much easier to write and debug, which probably looks something like this. Like you have this big digger, and then it's just using that little shovel there to get going. So that is some people we are wielding kind of the powers of machine learning just to do something very small and confined and like easy to get going with. Sometimes you might need it, sometimes you might not need it. I guess some of you are probably familiar with that. That is the Gartner hype cycle. That is probably the only thing that is true that Gartner is always bringing out, because everything else is kind of like just making stuff up, or at least it was always my impression that whatever the Gartner is predicting for the next 5 years is probably not going to be the way it will be. But the hype cycle is kind of like very, very true. Like you have some technology trigger, and then you have like this peak where everybody is saying like, oh, this will be so awesome and this will do all the things. I can still remember when everybody said that about NoSQL, and then people were kind of like, oh, maybe relational databases were not all that bad. And I have the feeling that kind of machine learning and AI and whatever you want to call it is kind of falling into the same perception every now and then. So you have some peak, and then you get kind of like a bit of a disillusionment, and at some point you maybe reach that plateau of productivity. Will machine learning or AI solve all your problems? Unfortunately, it probably will not. But that's probably no surprise. So anybody who has been in the field for some years knows, okay, all the promises, like everything will be solved by this technology. Unfortunately, it's not that easy, or fortunately, it's not that easy. Otherwise, nobody would need us anymore. So I want to talk about like a bit machine learning in general and like putting it in with AI and whatever. Then I will pick a domain of what we can do, since our use case is always about machine learning for ops data. I will use some ops data for that, and then I'll just play around with some data set for a quick finish. Let's see where we can go. So machine learning. There's always this misconception or this discussion like, what is artificial intelligence? What is machine learning? What is deep learning? How do they belong together? Is it all the same thing? Because some people always say, oh, it's basically the same thing. It's just like, depending on when people got started with something, they had to come up with a new fancy term. And that fancy term could be either AI, or if you came a bit later, it would be machine learning, or if you're very up to date, then it would be deep learning. I kind of find this very nice, this graphics. So you can see it all kind of started in the 50s already. Back in the days, I don't assume that most of you were around in IT back then, but maybe somewhere, or maybe a little later. So in the beginning, there was machine learning, and there were high hopes, and after some initial breakthroughs, people assumed, well, general artificial intelligence will be soon a thing. So general artificial intelligence will be like machines will be as good as humans at almost everything, and they will just learn one field by the other. And initially, it started as a very narrow field, like you would do something where machines would be good in one specific field, and then the idea was, well, we will just generalize that. And this will be applicable to any other thing afterwards. And you will just keep generalizing that until you're kind of on human level. Unfortunately, that didn't play out that well. And then in the 80s, we had, like, with machine learning, we had another wave of trying that. And then, like, in the 2010s, we had another wave of that with deep learning. Yeah. So the general purpose of general AI is always let's get something that is human level. This is something we have not reached yet. And we don't even have a proper timeline. Like in the 50s, 60s, and 70s, it was assumed like, oh, we will get there. But it didn't turn out that way, because in the 70s, there was the so-called AI winter. And this was also one of the reasons why you had to find a new fancier name, because a lot of people got burned by that they assumed, oh, artificial intelligence will solve everything. And a lot of money was pumped into that, and people wrote papers and plans and everything. And at some point, it didn't really work out the way people planned. So that was kind of like the first wave of AI. Then came the AI winter, and afterwards people came back with better algorithms, with more computing power. It's kind of like coming back in waves, and you're getting closer to your target. But with general AI, that's something we have not really achieved yet, and we don't really know when that will happen. What we are very good at right now is something like narrow AI, where you have one specific task, and the goal is to have something where you're as good or nearly as good as a human, for example, to identify an image. So 2 weeks ago, I was in San Francisco, and I uploaded this picture to Facebook. And then Facebook does that classification automatically for you. So for example, if you look in the meta tags, what Facebook does is it adds the alt tag, and it says like, image may contain, and then it's just guessing what could be in that image. And it's actually pretty good, because yeah, they have a lot of data, they have trained on a lot of data, and they're pretty good at just detecting what might be in your image. Even though I haven't told anything, like I didn't tag and say, okay, this is the Golden Gate Bridge. I've just uploaded the image without any other meta information. And the narrow AI in that case, like the image classification, that just kind of found or detected what might be in that image, and it's actually pretty good. Another thing you might have seen, which was pretty recent, is that Zalando is cutting some marketing jobs, where they're automating the marketing now, because previously they had a lot of handcrafted content. And now they kind of said, well, we can automate a lot of that with machine learning, where we can hyper-localize the content, where we know, okay, you're interested in these products and you're living in that specific city. And previously, somebody would probably hand curate the set of data or the products that might be interesting for you, or would write some content that is tailored for someone in a specific region. But they came to the conclusion with machine learning, this is much easier to do, or will scale much better, and they don't need all those humans anymore. So they now started to kick out some of their marketing people. Some will move to a different department, but a lot of them will be just kicked out, which sucks. And people are very afraid that, oh, machine learning will take over all of my jobs. Probably some, but probably also not all of them, because you might have seen this example as well, where some people used Google Translate to translate. Sorry for the German. If you don't speak German, it's some economic topic. And this sentence here is actually the very first sentence on Wikipedia if you look up Volkswirtschaftslehre, which is, yeah, an awesome German sentence. And this is what people got when they use Google Translate. Actually, I tried it yesterday evening. By now, Google got kind of cleverer. I don't know if somebody went in there to fix that, because people tweeted about that and it made the rounds. But by now, Google Translate got a bit smarter again. The sentence is still not great what you're getting now, but it's still got a bit better, and it's not just economics of economics and yeah, the same word over and over again. But yeah, having the fear that professional translators will go out of business like next week is probably a bit premature. We are not there yet. Like, it's kind of a general idea. Yes, you can do nice stuff, and if you don't understand some language, you can use Google Translate to get the idea, but it's probably not going to replace proper writing. So for example, our support team, when we do support in some localized language, we always say, for example, people in Japan don't want to speak English. And for them, it's super important to get support in Japanese. And we always say, yes, you will get support in Japanese during Japanese business hours, because then our people are online. But if you want to get help after hours, either you can write your text in English and somebody will help you, or we will use Google Translate. And we're actually handling support cases with Google Translate. And whatever comes out of Google Translate, we will try to help you with. And if it's no good, unfortunately, we will need to wait until somebody wakes up who speaks Japanese. Yeah. And then there's always this chatbot thing. I know that Vienna has this kind of, I always say, the chatbot bubble, because a lot of people are working in chatbots. I hope not too many are here and come with the pitchforks afterwards. But I had this thing once or twice where somebody came to me and I was talking to somebody and they were saying, I'm doing AI. And wow, that sounds super advanced. What are you doing? And then the people say, well, we're using this Facebook API and we're sending some data there and it sends us something back. And so we're doing AI. And I'm always like, you're doing APIs. It's just like the P is probably silent in your AI. Yeah. And I like to say, yeah, AI, APIs, kind of, it's very close. Some people don't make the distinction. We can have a discussion about that. But at least for me, when you say I'm doing AI, it's not just calling some Facebook or whatever API and get something back and use that. This is one of my favorite examples. I think this is the Poncho, one of the chatbots which you can ask, like, what is the weather like? And then you can see, yeah, it's working well or not that well. And I get the idea that it's trying to be cute, but like cute is not the main thing I want if I want some information. Like just because it's trying to speak French or saying it dozed off for a few seconds, that doesn't make something very smart or intelligent. It might be cute at first, but if I want to get some information, this is not going to make me very happy. Or something else I recently had, I'm using A1 Telecom, and I recently called their hotline. And normally, you know, you dial in and then you need to press 5 for that service and press 3 for whatever. And they didn't have that anymore. They had the whole thing voice automated. So you would need to speak to the system. And it didn't work at all. Like, my internet was not working, and I was trying to, in various ways, to describe like what my problem was. And even when I said internet, it would say, oh, you want to know something about your bill? And I'm like, no, that's not what I want. And then you do like 5 circles or so, and in the end, you could get back to that dial like 5 to get support for your internet or whatever. So yeah, the future might be very bright about all these automated systems and voice control and chatbots and whatever, though sometimes they're super annoying, or maybe I'm just too old and grumpy by now. Anyway, then there's this other thing. Maybe you've once seen a stateless chatbot, which makes for great conversations, because it just knows the current sentence and it doesn't have any context. Context about what? Which is another kind of common problem. This is solved. You can totally do that, but like simple chatbots will not be able to do that because, yeah, life is hard. So what is machine learning after all, kind of together? So you basically have an algorithm that can work with some data. You can kind of learn from that, and then you make some determination or prediction out of that data. So it's basically a trained machine. You haven't hand-coded the rules. So for example, one common example could be like classification of spam emails. Initially, people would write rules like, if there's something like, I'm from Nigeria and I will send you 100 million. If you detect something like that in an email, there's a very good chance that this might be spam. But of course, people are clever and they will reword stuff, and then it's kind of like, it's something 0.5 billion, and it's not Nigeria, but some other country. But so people will find various ways around. But with machine learning, you can actually not kind of write these rules explicitly, but can just learn like what does a spam email look like, and probably can find out these are the different kinds of spam emails. Like these are the ones who want to sell you Viagra, this one wants to get your money, and this one is just some plain annoying thing. Yeah, and this is the proper definition what machine learning is, but you will not get any venture capital if you just write this, because it sounds very dry. You learn from some experience with some class of task, and then you perform some measure, and then the performance at that task improves with the experience. The more experience you have, the better the machine learning should get. This is kind of like what happens. This is kind of the algorithmic view. But again, this is not getting you any venture capital, or you cannot build a startup just based on this one sentence. What machine learning is generally doing is something like, it's one of these four categories commonly. So you could have some classification. So you could have either like a binary classification, yes, no, or you could have a classification which has kind of like more outputs. For example, you could have a picture of somebody, and then you could try to do a sentiment analysis, like, is this person happy, sad, angry, whatever, and then your algorithm tries to classify what kind of facial expression does this person have. So that could be a classification. Then you have regressions, where you basically try to know or calculate what a specific value will be in the future, which could be like a temperature or a stock price, where you do the prediction of, oh, the stock prices will go up or go down. You can do ranking. Ranking is pretty much like you search for something, and then you don't just have the hits, but the system learns over time like what is a good hit, and you kind of like feed back information of what is a good hit into that search system, so that your ranking will improve over time. And then clustering is just putting stuff that belongs together, or is in kind of some groups that make sense together. You just try to classify similar things and then say, okay, these are all the things that are in that classification, or not, or clustering. Yeah, this is what machine learning might look like. That one machine is teaching the other little machines of what it knows, or at least that's how we humans do it pretty much. Yeah, would be nice like if it was like that. So the most common thing is when people say, oh, we are leveraging machine learning, is that they're doing linear regression. So basically, you have some information. These would be like the little dots, and then you want to find the linear regression, which is basically this red line, and you try to optimize that line and try to keep the distance of all these dots as close as possible to the red line. And the more data you have, the better that line can be, and the more you kind of get to the value of what makes most sense for your data set. So if you have like very sparse data and you only have 3 or 5 points, you will have a very coarse linear regression. If you get have lots of data, the linear regression can kind of optimize much better for all the data points you have. And if people are just saying, oh, we're doing machine learning, oftentimes it just means, yes, we have this linear regression, which is not all that fancy, but it can still do meaningful stuff for you. Yeah, whenever people say that, assume if there is no other information, it's probably a linear regression and not something more fancy. And then you can still make the distinction between supervised and unsupervised machine learning. Supervised machine learning is you have labeled data. So you have some input data, and then you have some output. And you know this is, for example, with spam emails, if enough people have said, like, this is spam, this is not spam, you have a huge data set, which Google probably has, and they know this is a spam email and this is not a spam email. And they can turn on that data because they have some supervised data where they know these are the inputs, these are the outputs, and then you can take a lot of that data to for your training data, and then you can keep some of the remaining data for your test data. You could do the same for unsupervised machine learning, where you don't have any annotated data. You just try to find some hidden relationship in your data. So you don't know what is actually, is this good, is this bad, is this an anomaly? You just have data, and you try to find some relationship out of that. Though finding relationship in data can be kind of tricky. There's this very nice XKCD comic, which I've broken up for better readability here, where somebody says like, oh, jelly beans cause acne. And then the scientists have to investigate, even though they just want to play Minecraft. So you can see that was kind of like 1 year ago, whenever Minecraft was very popular. So at first they say like, no, like with a 95% confidence, we can say like, no, acne is not caused by jelly beans. And then somebody says, well, but I have heard that it's just a specific color. And then they do the test for all the different colors. And it's a bit hard to see, but all of them like, no, we found no link. And then there is the one where it says, whoa. And there it says, oh, there is like a link. The problem is if you have like a 95% confidence interval and you make and you run the trial on 20 different data sets just by the mathematics, one of them will then be kind of true. And then you can write a big news article. The green jelly beans, obviously, were causing acne with a 95% confidence, and only 5% chance is in there. But that's kind of like if you run that same thing 20 times, there is a chance that, well, with 95% confidence, one of them will fire if you run it just 20 times. And that's pretty much what is happening here. Then you can do reinforcement learning, where you basically have a feedback loop. So whatever your outputs are, you're kind of continuously optimizing that on the feedback you're getting. So for example, if people are saying this is helpful, this is not helpful, you can then keep optimizing whatever your machine learning algorithm is doing. And then there is deep learning, which is, you have the neural network, which is also very fancy nowadays, because now finally we have enough computing power, or mainly good graphics cards, to calculate those, to basically calculate a probability vector, and you have lots of training and then parallelize that. That is, if you get enough graphics cards to actually do that, and they haven't been sold out to mine bitcoins before. Which is kind of sad that people are using all that computing power for mining some cryptocurrency. But yeah, that's a totally different topic. So what basically happens here, this is a very simple example. You have slept X hours the night before a test, and you have studied Y hours before a test, and then you try to find, like, what does this mean for your test score? Like the green thing on the right-hand side, that is basically the outcome of the test score. And then you have, with these two inputs, like they are weighted, like how important is sleep, how important is how much time you have spent studying. And then you can have one or more layers. The more layers you have, the deeper it gets. Or as soon as it's multiple ones, then you will have deep learning. And they're kind of a hidden input. So you can see it says mysterious. You don't really know how the system behaves in there. You just have some weighted inputs. And then at the end, some value plops out and it says, okay, if you've slept X hours and you've studied Y hours, your test score will probably be, I don't know, you will pass or you will not pass, or you will probably get that grade. So that is what you can do with neural networks, which is also very common, for example, for image classification. Or the standard example that a lot of people have is like, you have this detection of handwriting. So people write the numbers from 0 to 9, and then you try to detect each image or each number and try to defer, like, okay, which number could that be? And then you can extract some characteristics of each number, and that is what makes up your neural network. And then we'll say, okay, this was the number 5, for example, for whatever reason. What is really most important there is to have some big data set, because you will always need something to train there. So companies like Google, Facebook, Amazon, they have a huge advantage because they just have a shitload of data to work with. So for example, when people are now surprised, oh, how can Facebook be so good at detect stuff? Well, you have helped with their training data for years and years. So this is, if you have been on Facebook for a long time or a long time ago, probably this was what it looked like 10 years ago or so. It didn't do any machine learning back then. But what you could do is you could upload a photo and you could tag people. And you could just say, okay, this is that person. And that gives Facebook actually a huge amount of data, because it knows now, okay, this there is the face of a person, and that's probably somebody who is male. And from the profile of that person, they know like the age, the gender, the ethnicity, whatever. So it knows a lot of information and can use all of that information later on to then train its machine learning. And that's an advantage that you have given kind of to Facebook and all these other big vendors who can build cool stuff. And it's very hard to replicate that for you because you don't have this huge amount of data to work with. So yes, you can make data great again, but only if you have huge data. That's the one thing you really need. Yeah, and that's what the big companies are doing. And then people are like, oh, AI, ML, will I just use them interchangeably? And it really depends. Like, for example, when you're raising money, then you want to call it AI. When you're hiring, then normally people say machine learning. That's also some distinction I have seen. Or some people have framed it differently. They say, when you're fundraising, then it's AI. When you're hiring, it's machine learning. When you're implementing it, then it's just a linear regression. And as soon as you're debugging it, it's back to the good old printf. So like all the fanciness you have kind of at the start is going kind of like down, down, down until you're back at the basics. So while it sounds very fancy and it can do some cool stuff, some basics are not going away. Or there are these Kaggle contests where you have some problem and you try to solve the problem, and at the end you might win, I don't know, $1 million depending on the Kaggle contest. So what people are doing is we're just starting a competition, we are using some machine learning on it, and at the end we will profit. But normally you won't really get the profit, you will mainly get some disappointment. Because what is still totally relevant is that you will need to know the domain and need to know what it is about to optimize that. It's not that you can just throw some generic machine learning on it and then it will magically find out what is just the right thing to do and will make you rich. Unfortunately, it's not that easy. Okay, so enough making fun of machine learning. Let's do something more productive. So since I have an ops background and our product does work pretty well with that. I've picked something so you have some trend over time. And we try to determine some pattern in our data. So for example, this could be people visiting your website. This could be traffic. This could be error messages you have or HTTP return codes you have. All of these, you can try to find some pattern in data like that. So the first one is you have some trend, which is just like it's growing linearly or it's kind of like falling linearly, or you have exponential growth or whatever. Anything that is not stationary. So if you just have some stable value, you're not going to find out any trend out of that because, well, no change. Then oftentimes you have some cycles in the data. Cycles would be the days of the week. So Monday to Friday, you have kind of the same traffic patterns, for example. Saturday, Sunday will have totally different traffic patterns, at least on the average website. You have some seasonality. So for example, you know, if you have some e-commerce shop, like Christmas will be much higher. I think like Amazon is making, or Amazon.com for shipping stuff, is, I don't know, making 50% or so of its revenue around Christmas, or at least some crazy number. So they just have a seasonal trend and they know, okay, November and December will be different than all the other months because everybody is doing their online shopping there. The one thing that is not great if you have machine learning is if you have like some irregular pattern where there is no real pattern, it's just irregular, because then you will not be able to properly find anything. Unfortunately, we cannot help with that. And then you often try to find anomalies in that data. So you have, for example, a point anomaly. A point anomaly would be, assume your bank knows how much money you get out of the ATM machine every time. So whenever you go to the ATM machine, you get, I don't know, let's say 50 euro. And you normally do that. And at some point, you get 1,000 euro out of the ATM machine. Let's assume that's possible. Then that would be a point anomaly, because normally it's always like you get money, you get money, you get money, always the same amount. But that one time is a totally different amount. So that would be a point anomaly. You could have a contextual anomaly. Where kind of the context doesn't fit in with the rest. The contextual anomaly could be like you have more requests, you have more CPU and memory usage in your system, but the number of requests is actually lower than before, or the traffic is lower than before. So you have some kind of metrics are pointing in one direction, but another one is kind of like in a different one. Then you have this contextual anomaly where kind of in the context of all of them together, it's kind of going the wrong way. And then you have collective anomalies where you have or assume that everything is going in one direction, but something is kind of like an outlier out of how the collective kind of direction is going. Then you can have breakouts. These are kind of like changes in your data, which are not really anomalies. They're just changes. Like you sometimes have a ramp up. For example, you make an ad campaign and more people come to your website. Then you probably see some shift where just more and more people are coming. This is probably not an anomaly, but the result of your ad campaign. Or you can have a mean shift, which basically you're deploying a new version of your software, and suddenly you only need half of the CPU anymore because you fixed some bugs or optimized something. That would be a mean shift, where you have like just like you deploy the software, it's just dropping to some other value, and that's kind of like the new baseline, which will always follow. Whereas the ramp up is just something that develops over time. Yeah. If you want to detect anomalies with machine learning, you basically have two options. You have supervised or unsupervised machine learning. The good thing is in supervised machine learning is okay, these are the inputs and these are then the outputs. The bad thing about supervised machine learning is you will need to have that annotated data. So somebody will have to kind of have gone through all of the data and said like, okay, with this input, like this is an anomaly now and this is not an anomaly. And oftentimes you don't have that data. So very commonly you don't have supervised, but instead unsupervised machine learning, where you say, okay, this is the input, this is the output, and we assume this is an anomaly because this is kind of different of what we had before. Yeah, examples out of the IT are you get suddenly a spike of 500s because somebody made a bad deployment, and okay, something is wrong, more 500s, something changed in our system, we need to fix it again. You could have something like security events. For example, you have some unusual DNS activity where you could do DNS exfiltration. For example, if an attacker wants to get out information out of your network in a very sneaky way, they could just call subdomains under their control with that specific information they want to get out in as the subdomain. And most systems don't detect that. But if you kind of like look at the DNS traffic, you can spot that, even though it can be pretty well hidden. Or you could have some business analytics where okay, generally we have these log entries or log events, suddenly we have something totally different. And then your machine learning will probably or hopefully pick that up and say, okay, here we have something that doesn't follow the regular patterns or events that we had before, so something must be off here. You could totally do visual inspections. Though we always say there are not enough interns in the world to monitor all the dashboards that you could build. Which, sorry for the interns, but that's probably also not what you want to spend your summer on. Especially if you have like some complex or fast-moving data. Yes, you can stare at the graphs the entire time, and after 1 or 2 weeks, you probably know, okay, these are the patterns that I'm expecting. But A, you can easily miss something, and B, that's probably not where you want to spend your time and what your time is kind of best used for. So for example, if you have this data here, this would be unique IP addresses which have connected to my system. Where's the anomaly? We don't really see one. We'll get back to that data. That is, these are actually logs from our own website where we have counted, or it's basically, it's an Nginx proxy, and we're just using the Nginx access log to see what is going on our site, and then to find anomalies of what is going on and what is not really going well on our site. So you could totally define some static rules then. The problem is, to define rules, somebody needs to know the system well enough to define the rules. You could have false positives and negatives depending on how kind of like narrow the band of alerts would be. And as soon as your system starts changing over time, you will need to adjust it. So if you have more visitors to your site, you probably will need to change your alerts on a kind of a frequent basis or adjust them to whatever your system looks like today. So if you want to set a threshold here, like what is the number of unique IP addresses connecting to your system, which values would you pick? Like, yes, you could say maybe here at the bottom, below 2,000 might be a problem. You could say that. And then you could say, oh, maybe more than 14,000 would also be a good threshold. But there's a huge gap in between. And you probably don't really see, like, is there anything going on in my system that is okay or not okay? Where is the anomaly? Like, yes, you can set the thresholds, but they will be super coarse-grained. Yeah, so we need some kind of machine learning. Let's see what we can do there. And yeah, normally, machine learning is pretty CPU intensive, or if it can run on a GPU, you can also run it on a GPU. Since all my demos are on my laptop, it's like running Slack or Zoom or whatever, which will also eat up all my CPU. So you can totally build it yourself. Some very common frameworks for that are TensorFlow is especially well known from Google, Keras, Scikit, and loads of others are where you can just build your own machine learning algorithms, or you have some data and basically you want to extract some value out of that and find your anomalies. So these are just very widely used tools you can use. How do you build that pipeline? kind of like the machine learning component, that is the fun part. And people who are data scientists will always say like, yeah, we're doing data science the entire day. But what they basically do is they probably spend 5 or 10% of their time on data science, and the rest is like 70% is probably of the rest of the time is like getting the data and cleaning up the data, and 30% is complaining about not having clean data. Yeah, because it's kind of a very common thing. You need to find the right data, then you need to prepare it in the right way so you can load it, and then you need to clean it up. You need a proper data storage system where you can keep all of that data that you want to keep around. And then you probably want to have some optimization algorithm to make stuff scale and make it fast. Yeah, and to have this expectation that your data will be clean and will work the right way is always kind of cute. So yeah, find a data scientist, ask them, and they will probably make a very unhappy face about data cleaning. But it happens. And then people always ask, like, which one is the fastest machine learning algorithm? And for all these performance things, this is my favorite comic, where you have, under similar conditions, you're testing two systems. We are testing the squid and the house cat, and we want to know which one of them is more intelligent or faster or more performant or whatever. And you just need to find the right scenario, because then your system will always win. This is really the number one thing. Whenever some company benchmarks their tool against some competitors, they will probably find one use case that is very good for them and very bad for their competitors. That's why I would not trust any vendor-based benchmarks. I would normally call them benchmarketing and not proper benchmarks, because, well, yeah, people do something like this. So if you ask me, like, which is the best machine learning algorithm, this is the answer. So what you generally want to do is, when you want to find some anomalies, you want to find out, like, what is normal, like, what is the baseline of stuff that happens. Here, for example, you could see we have the black line is some, I don't know, I think it's the data trends for the visitors on your website or something like that. And you can see there is this pattern where probably the first 2 are weekdays, then the next 2 are probably Saturday, Sunday, and then you have 5 more days which are probably a weekday again. And then you try to get that baseline of kind of what is normal in your system. So you normally calculate within some confidence interval, you calculate what is the upper and the lower bound. So the upper bound is here red, the lower bound is blue, and you're just trying to find a system that is getting closer and closer to the actual kind of curve or the actual value that you have, to get kind of like this dynamic baseline of how close are you getting to what you're expecting. And yeah, most of the data is normally distributed. Sometimes you're unlucky and it's kind of like paranormally distributed. That will totally throw off any machine learning. So if you don't have like a good regular distribution of your data, no machine learning for that will save you. Yeah, so this would be another example. So you can see here, we had the first 3 iterations. We didn't really know what the system was up to. So here the upper and lower bound is just like this light blue background. And the darker blue line is kind of like, this is the actual data that is coming in. But then after about 3 iterations, this system here has learned like what is the baseline and what is kind of expected of the values. And then you can see the band, the light blue band around the actual data is getting narrower and narrower. So it's learning what is normal in that system. And at some point you have these colored dots. The more it's in the red, the more of an anomaly it is. So you can, for example, see pretty much at the right-hand side, there is this where it's falling down. There is kind of like, this is an anomaly which would probably be pretty hard to spot otherwise in that system here. And the one thing that you need to keep in mind is that whatever your baseline will probably evolve. Unless you have a system that is super stable, which is not that common, is that depending on how much more visitors you have or whatever you change in your system, the baseline will change. And you should have a system that keeps learning the new stuff and ages out the older information so that it's not stuck on any older information. So here, yeah, I think it's even the same data. You can see 3 iterations, and then it kind of knows what is happening. And then you can see we have, since I shouldn't move out of the way, I'm not trying to head over all the way. Let's see if my laser pointer. So here you can see here, we have this anomaly, and you can see here, the system has also learned the anomaly. So it's kind of like expecting there might be something going on here. So it doesn't really, since it's not supervised machine learning, it's just learning what kind of is happening in the system. And it's then continuing that trend and kind of feeding that anomaly into the model for the future, and will keep up to date with whatever happened in your system. Yeah, that's another example where you can see stuff is happening, and at some point there you have an anomaly, and then it keeps learning. Like, it's aging out that anomaly again, because here you have the anomaly. Here it's expecting the anomaly. Since it doesn't happen, here the anomaly is getting smaller, smaller, and smaller. So the anomalies are kind of being aged out over time again as well. Yeah. You can have a single time series, for example, unusual traffic, where you can see, okay, this is the traffic pattern I'm expecting, this is what might happen. You could also break that up into multiple time series. So you could have not one metric, but multiple metrics you would be interested in. And then each of those would be modeled as an independent baseline. So you have a machine learning model for each one of them. So for example, instead of having the global traffic, you could say, I want to have traffic by country. And then you can see, you can break that down into different countries. And then you can see sometimes you just don't have traffic. For example, here in France, probably they had either a strike or a national holiday. You never know with the French. But something happened and nobody was online anymore there. So it can make sense to break that up into different intervals to see how that data is evolving. Okay, so as I said, I'm just using, for my example, I'm using from our own website some visitors. So it's just, I think, 1 month or so, or no, it's 2 weeks of data or something like that. It's pretty much the Nginx access log that you're expecting. So you can see you have some bytes that you have transferred. We did a geo-IP lookup, so we know, okay, this visitor here probably came from India. This is the approximate longitude and latitude where they have come from. And then you get like the other information that you want. So you see that was the remote IP address. They did a get and got a 200 back, though we couldn't extract any proper browser information from that. Okay, and since I always try to do at least something live, this is what this might look like. So for example, here you can see I have just taken January to, okay, 1.5 months, March, website visitors, which were like around 15 million website hits. And this is the general distribution. So you can already, from this data, you get a rough idea what is going on in the system. So you can see here, this was probably a weekend. These were weekdays, weekend again. So you get kind of the general pattern. Then you could see, this is just some default dashboard that we have. You can see where are people coming from? Like from where is your website being accessed? So you can see, for example, Germany and France are doing pretty well. If we zoomed in a bit more here, we could probably see Austria as well. But since I'm not online, my map data would need to load online. So here somewhere would be Austria. And then you can see, okay, these are the return codes of my data. Like, this is pretty much all the data you can extract from an Nginx access log. So this would be just the return codes you have. You could extract, like, these were the top URLs you hit. You see, since you have the byte sent, you see how much traffic your website was sending, and then you could also do like a breakdown of, okay, these were the operating systems that were accessing our website, and these were, I don't know, the browsers and their specific versions. So that is what you get in the Nginx access log. There is no machine learning necessary for that. That's just log parsing, so no major magic here. Then you could write your own visualization. So for example, this was the number of unique remote IP addresses that I've shown you before. And this was the bytes that we were transferring from our website, which they kind of correlate slightly, but not that strongly, for especially here, kind of there's no strong correlation to that one. Does anybody see the anomaly in the top chart here? Or should I let you stare at that dashboard for a week and maybe then you can see it? I think, if I'm not mistaken, the anomaly is this one here. So this downward thing. Though it's very hard to see. We can actually leverage the machine learning stuff now to see what is going on here. So I've quickly built 2 visualizations for that. The first one is about having a single metric. That is the same information that I've just shown you. That is the unique IP address that we had in our system. And you can see our system needs approximately 3 iterations to learn. So you can see here, these are the first 3 days. This was Wednesday, Thursday, Friday. And then the algorithm thought, well, I know what to expect. The problem was then we have Saturday, Sunday, and the traffic pattern is totally different. So you're kind of throwing off the machine learning algorithm here a bit, because that is here you're having your 5 days of the weekdays again, and then you have your weekend again. And you can see the pattern continues that you need about 3 iterations to learn a pattern, because weekend 1, weekend 2, weekend 3, about here it got the weekdays pretty well already, and here it also got the weekend then. And from then onwards, it knows, okay, this is kind of the weekday pattern that I'm expecting, this is the weekend, this is the weekday pattern, so the system kind of learned how stuff works. And this is here where we have an anomaly. So let's quickly see the anomaly. Let's zoom into our anomaly. And you can see here, something was happening. Like generally we would expect traffic in this area here, but somehow it was falling down. And each of these points is actually an anomaly, and it actually has an anomaly score between 0 and 100. This is how we modeled that, but you could totally build something similar. The closer it gets to 100, the worse the anomaly is, and then you could even have like the list which says like, oh, normally I'm expecting that value here, 1,400 something, I got only 86. So this is 17 times lower than I was expecting. And this was on the 27th of February last year. Anybody remembers what happened then? No? Okay, let's jump back to my slides. I think we have seen most of those already. That was when there was the first ever bigger S3 outage from AWS. And half of the internet basically relied on that. So yeah, S3 went down, and that affected a lot of stuff, including Amazon stuff as well, because they were also themselves relying on S3 to be available, like everybody else. So unfortunately, we had the dependency in our website, which basically killed our website and our downloads and a lot of other stuff. We then thought about, should we make some multi-cloud strategy or whatever? But in the end, nobody complained because half of the internet was down anyway. And if the internet, or if your own site is down and everything is on fire, nobody complains that your downloads are not working. So we kind of gave up on making stuff unnecessarily complex because there was just no point on that. But you could very nicely see that anomaly there. Yeah, we are nearly out of time. Okay. Then I will stick to slides. Then you can build the same thing with multiple models. Here, I have broken my data down into the response codes that my website is sending out. And then you can find further anomalies. So for example, here, I have an overall anomaly score that is like, the top one is kind of like, this is anomalies overall. The red things are where the anomalies are. And then you can break the entire thing down into the response codes. So you can see for the 404s, we have a band of trouble over there. This was, for example, on our blog, and we suddenly had a spike of 404s. This is when we published a bad link on our own blog, and suddenly the 404s started to spike. And this was when we had in our CMS, since we're using a CMS, and CMS are mostly crap, when we kind of broke some links internally unintentionally with a CMS change, you could totally see that here that we suddenly had this spike of anomalies where, yeah, suddenly stuff is not going well. You can have combine multiple models and see what they're doing. So here I'm combining, this was the remote IP addresses, the example which I've shown before, where you can see this was when our website went down because of Amazon S3. So this is here, that was the S3 outage because nobody could access our data anymore. And these are the 404s. And these two totally look correlated, right? So something is happening here, and then suddenly the 404s spiked. Unfortunately, these two events were totally unrelated because this was the AWS outage, and this was our own change on the CMS. And that will screw off or throw off any machine learning because it tries to learn and correlate some data. But if there is no real correlation, it will just be kind of like try to infer one which is not there. So yeah, correlation doesn't mean it's actually a causation. Everybody knows that, but always keep that in mind. And yeah, XKCD extracts the best. Once you take a statistics class, does it help to make the distinction? Maybe. Yeah. And then they're always like, what is the cause and what is the reason? or like what is the cause and what is the effect. So for example, for cancer, there's this very interesting study that in the US, the cancer rate has spiked and cell phone usage spiked afterwards. So here the theory could be that cancer is causing cell phones, which is also not the right thing, but if you just look at the data and misinterpret it, that is what you might get. Yeah. Any correlated features would mess up your system. There's unfortunately no way around that. Yeah. Final thing here, what you can also do is future predictions. So the yellow stuff here, these are future predictions, and you can see the further it goes into the future, the less certain they are, because the more coarse-grained the entire system gets. But this is very helpful if you like, I'm expecting this number of visitors, or this is the disk space I'm expecting in the future, or the resource usage. And this can predict for the future, like this is what you will probably have in your system, given that there are no other anomalies. Yeah, then you could start doing like categorized users, but let's skip that for today. So to wrap up, we've seen machine learning, domain where I picked like mainly ops data, and then some Nginx data set where I've played around with. If you want to know more about machine learning, one very nice paper I've seen is this one here, Best Practices for Machine Learning Engineering, which has some very nice rules. So for example, the rule number 1 is don't be afraid to launch a product without machine learning, because you might not need it. And then, yeah. If you can interpret the model properly, debugging will be much easier if it's not just a black box that spits out random data. And plan to launch and iterate on stuff. But it has 43 rules all about machine learning, which probably make sense if you build anything in that space. And yeah, and don't forget, maybe at some point machine learning is not the hot new thing anymore, but something else comes around. So yeah, Silicon Valley is probably heading somewhere else already again. Anyway, that's it. I think we're pretty much out of time. If you have questions, come to me, find me afterwards, talk to me. If you want to have stickers, I have loads of stickers here. So if anybody wants stickers, they're very nice. Take them. With that, I think we're done. Thanks very much. Wait. I'm always taking a picture because my colleagues don't know where I am. And this is my way to prove that I've been working today. Smile, everybody. Yeah, you can also wave. Thank you. Enjoy the break.